Thank you, Mr. Chairman. The title of my talk is Mind Reading Technology, BCI. BCI is a communication system that interprets and delivers users' intention to the external world without relying on any normal output pathway of peripheral nerves or muscles. So using mouse is, of course, it is not BCI because you are using your muscles. So using your eyes, eye mouse is also not PCI because you are using their muscles and some nerves. So I think there are many well-known interfaces, intention recognition interface, such as speech recognition and gesture recognition and facial analysis and so on. But I believe that BCI will be eventually the eventual goal of user intention recognition technologies. So recently there are some interesting projects, research projects. So last year, Elon Musk started a new company named Neuralink. This company aims to develop BCI technologies. At the first stage, he wants to develop technology for quadriplegic patients and people with some muscle and nerve disorders. And last year, Facebook started a new project named Typing by Brain. This project is aiming for typing 100 words per minute. Yeah, this is great if it is implemented. So until now, they say that they can enter 8 words per minute. They want to develop new technologies. So, and in Korea, the tire company named Hankook Tire started demonstrate a project named Neuro-Driving Mind Reading Tire Project. So they successfully demonstrate a simple car working based on the brain signals. So in these BCI researches, there are 2 kinds of brain signal acquisition methods. The one is invasive, and the other is non-invasive. Invasive method acquires the brain signals by implanting the electrodes directly into your scalp during neurosurgery, especially for people with paralysis. However, this is very challenging and very high-risk project, so people don't like that. So that's why researchers are developing technologies for non-invasive signal acquisition approaches. This has problem of the high noises. The problem with noises, but it is very suitable for real-life applications, mobile applications. So that's why I'm focusing on these areas. So especially the sensors, sensor devices, we are focusing on EEG. EEG, electroencephalography devices. This is very light compared to other non-invasive devices and very mobile. So before to move to our interesting applications, let me briefly introduce some representative paradigms, which is very important in BCI researches. The first one is motor imagery. Motor imagery paradigm is that a brain signal pattern caused by executed or imagined movements are used. That is, if you are thinking some movements, there are some special activities in brains. So you make the best use of such kind of brain activities in the development of your brain, in the recognition of your brain intentions. So for example, if you are thinking about your left arm movement in the brain regions corresponding to left arm area is highly activated. So by recognizing such kind of activities, you can recognize your intentions. The next paradigm is ERP. ERP is, we call it event-related potential, and this is based on a brain signal pattern that is generated after presenting some event or stimulus, like such as image or some audios. The next paradigm is movement-related cortical potential. This is a low-frequency potential generated by the planning or execution of voluntary movements. These potentials are generally occurred on movement-related brain regions in human brain. So this is well-known visual evoked potential. We call it SSVP, steady-state visual evoked potential. SSVP is based on brain signal pattern during concentration on a particular visual stimulation. That is, frequency components of the brain signals are increased on occipital lobes because the visual stimulus generated in occipital lobe area by the visual stimulus. So different frequencies of visual stimulation can generate various commands. The next one is somatosensory potential. We call it steady-state somatosensory evoked potential. Here, a brain signal pattern during concentration on a particular vibration stimulation is used. So spectral and spatial features are increased by tactile stimulus. For example, you can assign some 17 Hertz tactile sensors in left hand. You can assign 20 Hertz tactile sensors, vibrators in your foot. So by assigning different sensors, vibrators, you can generate different signals, signal patterns. So based on these simple paradigms, I would like to move to broad introduction to research development. The first one is exoskeletal robot control based on BCI. So this is a lower limb exoskeletal robot control system based on SSVP. VP means that we can decode users' intentions based on the visual stimulus. Visual stimulus means that we assign different frequency bands to different stimulus. That is, here we assume that we have 5 different stimulus, visual stimulus, so we assign different channels to the frequency band to different locations. So here is for right direction, we assign 15 Hertz. And here in the turn left point, we can assign 11 Hertz, something like that. So by doing this, we can design a classification system to control exoskeletons. So we can extract features and we can classify these input features, and finally we have 5 different kind of classification results. So as expected, so we developed the machine learning algorithms which can be applied to these applications to successfully decode user-intended signals under the ambulatory environment, because the exoskeleton robots should assume that this robot can move here and there. So we designed a deep learning architecture that can discover high-level or abstract patterns inherent in brain signals, thus robust to noisy or artifacts. This is the architecture we developed during these experiments. So we made a performance comparison with existing methods under the static and ambulatory environments. So our implementation, our proposed CNN-based method outperformed the existing method, and it is why. So clearly, the feature representation we used is they analyze the network decision. The network focuses, our network focuses on the stimuli frequency components as well as the harmonics. You can see 9 Hz, 11 Hz, 13 Hz, 15 Hz, 17 Hz. So this shows that our feature representation power is very good in this implementation. So let me show you a simpler demonstration. Oops.
Researchers have developed a machine that could read the minds of the disabled and transform their lives. When used in combination with an exoskeleton that enables movement, the brainwave interface measures EEG signals and then decodes them into motion control orders. Professor Lee Sung-Won and his team at Korea University are behind the development.
The exoskeleton robot reads the brain waves of the user and removes unnecessary external noise through the signal processing system. Then, the robot picks out and classifies the certain characteristics of the brain waves. In this way, the exoskeleton robot is controlled by matching the classified brain waves to the designated orders.
To do that, a visual stimulus generator is used to read the brain waves.
Okay, let's move to the next topic. So the next research based on BCI research is arm control, robot arm control. This is a arm control system based on decoding 3D trajectory of imagined arm movement from EEG signals. So we developed a robot arm control system which can predict the trajectories of imagined arm movements. So we improved the online performance by detecting movement onset intentions. Let me show you some experimental result. So the experimental procedure is, first we execute and observe movement trajectory in the shape of infinity symbols. So for comparison, we used two different kind of decoding models. The first one is multiple linear regression that was used in previous study, and we used the kernel-rich regression, which is non-linear regression method. So comparison of measured velocity and decoded velocity during actual and imagined movement shows that our KRR, kernel-rich regression, achieved higher accuracy than traditional multiple linear regression. We have a very simple experiment. So because our intention is not feasible, we made some scenarios to generate trajectories. So after trajectory decoding, the robot can generate the same movement, the trajectory movement, so we can compare the performance of the actual robot systems. So the next one is wheelchair control. So we developed a wheelchair control system based on the SSSEP. As you may know, the SSSEP is based on the concentration toward the vibratory stimulus. So we designed we attached the vibratory stimulator with different frequency to both hands, two hands, and foot. For example, for forward, we assigned to the foot, and for left hand, for right hand. So we extracted the special frequency features for detecting intentions after FFT and CSP pre-processing. So this shows the result of future control experiments. So we extract the highest peak value at the stimuli frequencies, which are consistent with the neurophysiological knowledge. So we demonstrated the possibility of SSSEP-based wheelchair control systems. So let me show you the demonstration. So this is the working system of our SSSEP-based wheelchair control systems. So actually the speed is not so fast. This is 6 times faster to actual speed. So it is not stable yet, but we need to improve sooner or later. So the next technology we are developing is Neuro-Driving. So Neuro-Driving is a new technology that helps a driver with the function of controlling a car on his or her intention and perceiving diverse situations, including emergency, by means of brain signal analysis. So according to the neurophysiological studies, the braking based on physiological response is much faster than one based on the normal behavioral response. For example, in the case of driving in highways, the difference is 3.6 meters when you are driving in 100 kilometers per hour. So near 4 meters is rather very big distance. So we want to detect drivers' braking intentions based on BCI. So we performed emergency braking based on EEG analysis prior to actual braking based on behavioral response. So we hope that this will prevent critical traffic accidents caused by delayed braking responses. So we classify 2 kinds of braking intentions. The one is emergency braking, and the other is normal soft braking. So we designed the system like this way. So there can be 2 different situations. One is normal soft braking. Soft braking means that you can decelerate your speed, and the other is emergency situation. You want to reduce your speed very fast. And by using machine learning techniques, you can classify your intention automatically, and according to the result, classification result, if your intention was soft braking, you can generate the actual braking, and then otherwise, if it is urgent, it is emergency braking, you make necessary braking situations. So this is apparatus. So we designed the driver simulator with 3 wide screens, a steering wheel and the accelerator and the brake pedal and the seat. So for generating random driving stimulations, we used the Unity 3D engine to design our driving stimulator generator. So this provides a high level of customizability and excellent degree of realism. Also, high availability by a huge amount of presets from SSSEP. So here you can see the screens, and this is actually the driving systems. And here there are 3 kinds of random emergency situations that generated. Of course, the driver doesn't know which kind of inputs will generate in next few seconds. It's randomly generated, so the EEG signals are computed from his head, and this is analyzed, and we make a closed loop analysis. So this is the system. So this demonstrates real-time implementation. That is, when you are driving, you can control your speed of your car in real time. So we tested our systems with different kind of random emergency situations, and our system automatically decreases their speed without any problem. This is our implementation. So we are implementing our system to real car. So we are working with the Hyundai Motors. So this is the test bed. So we, based on our experience with the simulator, we moved to the real cars. So we are gathering the data from the real human driver, and so by generating the emergency situations, we hope to stop in emergency situations. So this is data gathering stages currently. So we hope fast emergency detection based on brain signal analysis will be possible much faster than actual braking. So this is a Cybathlon project which was held in October 2016 in Zurich. So here we had 6 different kind of disciplines. So one of them was BCI-Race. So in BCI-Race, the participants have to pass 4 kinds of obstacles with different user intentions. So that is walk, run, jump, roll. So they have pre-decided classes of obstacles. So we implemented the CNN-based 2-layer classification systems, real-time systems for processing this kind of obstacle recognition and avatar controls. This shows the videos. So this is our team. He's a tetraplegic patient. So this is our team in tournament. So he played very well at first, but finally he made a mistake. So unfortunately, the result was not so good. So Swiss was very good at then the final race. The final race we were 6th, but the score was not so different. So next research is Ear-EEG. Ear-EEG PCI is, I think that this will be much convenient and user-friendly, unobtrusive, if you can make the earphone or headphone-like interfaces without using scalp EEGs. So that's our hope. So we are working on estimating brain signals based on Ear-EEG. So we are developing a regression analysis method between Ear-EEG signals and the scalp EEG signals on visual motor areas currently. So estimating EEG signals on visual motor area using analyzed regression models is our current main work. So here also KRR, kernel-rich regression-based analysis method is under investigation. So the basic idea is that, okay, if you have a visual stimulus here, we don't like to use, if we assume that we can't use this information. So if you are using Ear-EEG, around the Ear-EEG channels, okay, the performance will be much poor than using your visual channels. So our belief is that by analyzing the relationship between this visual area and Ear-EEG area, ear area, so we can estimate EEG signals on motor area using Ear-EEG signals. So this is our pilot study. So we made a simple speller experiment using the visual stimulus channel, visual channels. So in OZ channels, so you can do some performance, you can get some performance. But if you are using only ear channels, around the ear channels, the performance is not so good. It drops to near 60%. But if you are using KR rich regression with based on the Ear-EEGs, so the performance is increasing, and of course it is not so good as the visual stimulus, but performance is rather compatible with the using visual stimulus areas. So this is our result. So the next one is our BCI research for analyzing level of consciousness based on BCI. So we want to analyze brain network properties according to the level of consciousness. On EEG-based conscious state analysis system for reducing diagnostic error is much important, I think, because approximately 40% of diagnostic error during estimating patients' conscious state in anesthesia surgery happens in usual hospitals. So we want to observe functional brain connectivity changes in the 5 different kinds of conscious states: baseline, transition into unconsciousness, transition into consciousness, and recovery. So we gather data from anesthesia surgery hospitals. So the participants, we gathered the participants for 60 subjects, participants, and we used 2 different kinds of anesthesia techniques, propofol and midazolam, and we used some equipment for brain signal measurements, EEG. Also, we gathered functional NIRS, near-infrared spectroscopy, and of course, we used the bispectral index, PIS device. So our finding, so the results was that we observed a highly increased connectivity in the delta band during unconsciousness compared to other states, and highly increased connectivity in the beta band during transition into unconsciousness and transition into consciousness. So this is our finding. So the data we gathered, so 실제로 actually this is baseline state, and we are moving to transition. We are transiting to unconsciousness, and after some time, we are moving to unconsciousness state. So after some time, so we are back to transition to consciousness state, and finally recover to normal state. So the last topic I want to mention is the explainable AI. This is one of the active research area nowadays. So the traditional AI system is, okay, you have a trained data, and you have a machine learning, and you have a finally classification system or learned functions. However, this learned function cannot explain something. They don't know why they did such kind of classification. When they can succeed, they don't know. When they fail, they don't know. So they want to develop explainable models and explainable interfaces for interpreting or for explaining something. So in the case of BCI, this is critical because BCI is non-visible. So in the case of vision in images, you can see something. It's very easy to explain, but unfortunately, in the case of BCI, they cannot. It is non-visible, so that's the problem. Also, BCI is very difficult to for classification because it has a very high intra-subject variability. Even for the same person, the variability is very high, and this shows the intra-subject variability of EEG signals. This is very challenging issues. So recently, LRP is developed by Klaus, and this is the method that identifies important pixels by running a backward path in the neural network, traditional neural network. So LRP decomposes the classification output into sum of pixel relevance score. So usually the classification is, machine learning is, if you think there is a feed-forward step, then this is, LRP is something like the feedback steps. So finally you can generate some kind of heat maps. This shows the result of LRP compared to sensitivity analysis, previous sensitivity analysis for the input data. So we are developing the integrated framework for integrating CNN with LRP. So EEG signal is classified using the extended 3D CNN architecture. The 3D CNN means that spatial temporal spectral domain architectures, not just the 3D, but multispectral spatial temporal spectral domains. Also, the extended 3D LRP is proposed to explain the classification output of a single trial. If you have multi-trials, it is not so difficult, but we want to emphasize that we can we can explain the classification output even for a single trial based on this 3D, from the 3D CNN outputs. By doing that, finally, you can explain something with topography based on the relevance scores. So this is the usual traditional classification pattern recognition system. You have output. But the next step is explanation interface. By doing this, we can visualize your classification. So this is the result. So topography based on relevance scores are consistent with the neurophysiological evidence we know. And spatial patterns of our method are consistent with the ERD phenomena, which is related with sensory motor brain activities. This shows a simple left and right classification explanation. Okay, so this is my last slide. So I think that we need to work on more brain-inspired artificial intelligence. This is my hope, and thank you very much.
Thank you very much, and we now have questions. May I ask a question? What is the rate of information that can be deduced from EEG? The rate of information that you can deduce from EEG?
You mean the rate of information?
Yes. How much information can be deduced per unit time using EEG? Can you evaluate that?
No,
can you estimate that? No.
I didn't have such kind of experiments. So usually we have 1,000 hertz data.
Yes, yes.
Oh, sorry.
Yeah. So the rate of sampling is 1,000 per second.
Right. Yeah.
But how much can you actually get into information? Is it measurable, or is it?
Sure, at the level.
Yes.
At the sampling rate, we can acquire the information. Yeah.
It depends also of the number on the number of channels.
Yes.
The more you have captors, the more you
usually we have 64 channels, but if you wish, you can increase it up to 128. But usually 64 channels are enough, we think. But if you wish, you can increase it, or if you wish, you can decrease it. 32 channels and 16 channels, it depends. But the location, which locations are optimal is depends on the application dependent. It's application dependent.
When you limit the number of sensors to the region of the ear, how many channels do you have then?
Currently, we have 18.
80.
Ups. In 9 channels in left ear and 9 channels in right ear. So sometimes we decrease to 7, but maximum we have 9 channels in our current experiment.
Evoked there. And Odile Mac.
I'm afraid my questions will be somewhat naive after this very stimulating talk. Nevertheless, you are using non-invasive
Yes.
methods. This is exactly the question which was asked by our chairman. Why don't you try to use invasive methods? Because you are dealing with patients who are very disabled, tetraplegic patients, paraplegic patients. They would probably accept an invasive method, I assume. And keeping in mind that in 1 cubic millimeter of cerebral cortex, you have something like 10,000 to 15,000 neurons, and perhaps 500 million of nerve terminals, you would obviously increase very much the specificity of your results. So I would like to ask you a medical question, in fact.
Yes.
For the future, what would you expect for our patients? Would you expect to use this type of method, or do you think we should increase the specificity and the strengths of invasive methods?
Yeah, I think it's very difficult to answer to your questions because for patient applications, so we work with the doctors more closely with doctors, and in the case of invasive researches is also people, they don't like the invasive operations. So my main focus is on non-invasive application because it is very easy to make experiments compared to patient experiments. That's the main reason. But I think the patient-controlled experiment is also very important, and the technology will be much simpler than non-invasive signal processing approaches. But we need some collaboration with the medical doctors. So did I answer correctly to your questions?
Not exactly. Intuitively, I have in mind that if you are really activating or recording a small amount of neurons, small amount of networks, neural networks in the very restricted areas of the cerebral cortex, then you would increase the specificity and the bruit. You would decrease the non-specific bruit which is recorded. But I don't know. I don't have the answer myself.
Sorry.
Odile Mackey on that side here.
Thank you very much, because this is a very bright presentation. I am really admirative.
Thank you.
Very beautiful. Maybe my question is irrelevant, but I am wondering how many human resources you have in your laboratory to do such beautiful experiments?
Yeah, currently our graduate students have about total 50. But for experiment, we are gathering additional human subjects outside of our lab. So usually we pay for their participation. So usually we are using more than 100 human subjects outside of our lab. Of course, for some experiments, we are using inside our lab graduate students to make experiments. But usually for controlled experiments, we invite the human subjects outside of our lab.
But among the 15 people of the lab, they are all researchers, or you mean also technician staff, in addition of these 15 people?
Mostly they are graduate students, master students and PhD students, and 3 postdocs. And so there is no technicians. So my master students and PhD students, they do technician roles together during experiments.
Still more congratulations.
Olivier Faugeras.
In order to go a little bit in the directions suggested by Evoked,
Yeah.
I was curious to know if you tried to do to solve the inverse problem, do the source localization.
Yes.
Have you tried this?
No. So
Too expensive?
Yeah, and also too expensive or very difficult problem. I think it's a very difficult problem. So I think in the case of most of EEG research, in the case of other devices like functional MRI and other researches, they have very accurate source localization researches. But in the case of EEG, it's also very important issues. But there's not that much reported papers on the topics. But I think that it's very difficult also topics, top problems. Yeah.
Stéphane Mallat.
Yes, I suppose that you need a lot of learning for a patient in order to be able to do that. So is there any transfer from one patient to the other? In other words, does it have any stability so that once you have a learning from one patient, you can use that and have a second patient being able to activate relatively easily the system, or it's again a long and painful relearning process?
So you mean something like transfer learning issues?
Transfer learning, or the fact that you do have a stable learning from one patient to the next?
Yeah, I think it is very also top problems. Transfer learning and one-shot learning or zero-shot learning is one of the topics we are studying recently. So currently, up to now, we don't have any result for such kind of transfer learning experiment for our applications. Sorry for that. But we are studying about that issues nowadays.
I think we'll have to stop at this point. Thank you again very much.
Thank you.